Okay, so without further ado, Angela is a board director of tech and ops chair for Women Who Do Data, and she's here to present us the paper Self-Consuming Generative Models Go MAD.
Yeah, thank you so much. So, as Lindsay has indicated, I'll be presenting Self-Consuming Models Go MAD, and I will be dedicating this presentation to my boyfriend, who's actually one of the authors of this paper. And his name is pretty much bolded in this poster as well, just as an indication. So, due to the rapid progress of generative AI, there has been a rapid rise of synthetic data for imagery, text, and other data types. Due to this phenomenon, and since training data from the internet tends to be sourced from the internet, there has been an increase of synthetic data being used as part of the training set for today's AI models. While this does not sound ideal, there are reasons why synthetic data is being integrated as part of training data for AI models. First, it can be easier, faster, and cheaper to use synthetic data for use. Second, it has been found that data augmentation can boost AI system performance. Third, synthetic data can protect privacy, especially in sensitive applications such as healthcare. And fourth, and most importantly, as deep learning models become increasingly large, we are running out of real data on which to train on them. However, a glaring issue with the use of synthetic data for training AI models is that repeating this process for generation after generation of models forms an autophagus of self-consuming loop whose properties are poorly understood. Also, depending on how the synthetic data is generated, sampling bias can happen where synthesized data is cherry-picked to trade off perceived quality, as in the data looks or sounds good or precision, versus diversity, as in the different types of data generated or used or recall. To investigate this problem, the authors of this paper conducted an analysis using state-of-the-art generative image models of 3 families of autophagus loops of varying types of real data availability through generations of training. Also, to account for the additional issues that can happen in this scenario, the authors also investigated whether samples from previous generation models have been biased to trade off data quality or precision versus diversity or recall. A hypothesis that the authors developed to conduct this research for the paper is that synthetic data contains fingerprints of generative architecture that may be reinforced by self-consuming generators. Each generation results in a progressive amplification of cross-hatching artifacts, which are similar to aliasing in style GAN2, a generative adversarial network. However, in another direction, autophagus loops featuring generative models tuned to produce high-quality synthesis at the expense of diversity might progressively dilute the diversity of the data on the internet. To understand the autophagus process and its potential consequences better, one can turn to mathematics and biology. In mathematics, an autophagus loop is a contraction mapping that collapses to a single boring point, while at the other extreme, it is an unstable positive feedback loop that diverges into bedlam. In biology, mad cow disease, which inspired the name of the phenomenon that the authors investigated, is a fatal neurodegenerative disease that resulted from a practice of feeding cattle with remains, including brains of other cattle. Before diving deep into the 3 families of autophagus loops that were conducted in the paper, we must define an autophagus generated process first, with the MAD generated process. An autophagus generated process is a sequence of distributions of generated models where each generated model, GT, is trained on data that includes samples from previous models, while a MAD generated process is a sequence of distributions of generated models that follows a random block such that the expectation of the distribution increases with time. With that being said, the authors claim that under mild conditions, an autophagus generated process is a MAD generated process. The authors also state that 2 critical aspects can drive an autophagus process MAD: balance of real and synthetic data in the training set, and the manner in which the synthetic data is sampled from generated models. The paper proposes 3 types of autophagus loops that realistically resemble the way real and synthetic data are combined into autophagus training data sets for generated models. Fully synthetic loop, where the training data for each generation's models consists solely of synthetic data sampled from previous generation's models. Synthetic augmentation loop, where the training data for each generation's models consists of a combination of synthetic data sampled from previous generation's models, plus a fixed set of real training data. And fresh data loop, where the training data for each generation's models consists of a combination of synthetic data sampled from previous generation's models, plus a fresh set of real training data. To implement cherry picking to explore the roles that quality and diversity play in driving an autophagus process MAD, the authors of the paper use bias sampling methods that are commonly used in generative modeling practices, such as the truncation in BigGAN and StyleGAN, guidance in diffusion models, polarity sampling, and temperature sampling in large language models. To determine whether an autophagus process has gone mad or not, the authors use Wasserstein distance through the Frechet inception distance, which measures the minimum work required to move the probability mass of one distribution to another. Precision, which is the proportion of classified positives that are true positives, is used to measure the quality of the dataset, while recall, which is the proportion of true positives that have been classified as positives, is used to measure the diversity of the dataset. Through the fully synthetic loop, it is found that without sampling bias, the quality of synthetic data or precision decreases. But with sampling bias, the precision will increase, but the diversity or recall will decrease rapidly. Overall, the fully synthetic loop shows that if exclusively training on synthetic data, either the quality or the diversity of the generated model either decreases over generations. Through the synthetic augmentation loop, it is found that a fixed real dataset only slows down generated model degradation and not necessarily prevent it completely. Overall, the synthetic augmentation loop shows that fixed real training data only delays the inevitable degradation of the quality or diversity of the generative models over generations. Finally, through the fresh data loop, one of the most interesting findings from the fresh data loop is that initial models will eventually be forgotten in the fresh data loop, since at every iteration of the model, new fresh samples of real data are fed to the model. Another interesting finding is that the performance of the model depends on the amount of synthetic and real data used, especially with synthetic data as summarized through phase transition. Limited amounts of synthetic data can improve performance, while too much synthetic data can hurt performance. Overall, the fresh data loop shows that with enough fresh real data, the quality and diversity of the generated models do not degrade over generations. The authors of the paper recommend practitioners to use the aforementioned results and analysis as a warning to remind them on how much scarce real data is necessary to avoid madness in the future, and take deliberate care to make sure that all anonymous synthetic images are artifact-free and diverse, and that real data is present in the training as much as possible. To maintain trustworthy datasets containing exclusively real data, it is recommended to develop methods to identify synthetic data that can be used to filter training datasets to reject synthetic data, or maintain a particular ratio of synthetic to real data. Another recommendation is to watermark synthetic data so that it can be identified and rejected when training. To conclude the paper, through conducting the autophagus loops, the authors conclude that without enough fresh real data each generation, future generated models are doomed to model autophagy disorder, or MAD, where either their quality or diversity will progressively degrade and generative artifacts will be amplified. The worst case scenario that can happen is that MAD can poison the data quality and diversity of the internet. That being said, it is inevitable that as to now, unseen unintended consequences will arise from AI autophagy even in the near term. One future direction that the authors can see to extend their work is possibly study combinations of the autophagus loops proposed in this paper. Another future direction that the authors can see to extend their work is to investigate how distance between synthetic and reference data manifolds will manifest itself in lower performance on AI tasks such as classification. While the work in the paper is focused on image datasets, the authors claim that their findings can be applied to any dataset. And that's